Just a quick video to go over the solutions for the 5-1 Part 2 homework here, looking at Riemann sums. So one of the things we said in class when you're doing a multiple choice question and you're going over, kind of identifying which Riemann sum represents the area approximation correctly, we want to look first at that delta x, the width of each subinterval. So that's what I'm going to do first for number 1 here. So we're given this function, and we're going from x equals 4 to x equals 6, 4 equally spaced subintervals. So then my delta x should be 6 minus 4, the length of the whole interval, divided by 4, which is then 1/2. And certainly you don't need to show that work. So that's the delta x, the width of each subinterval, the width of each rectangle that we can then factor out. So as I look at my answer choices here, I need a 1/2 being multiplied by everything here. So immediately I see some of them have 1/4. So I'm thinking it's not going to be those ones. So I'm going to go ahead and kind of, I don't want to be too aggressive because I might change my mind later, but I'm thinking it's not that or that. I like that there's a 1/2 for the width that's been factored out. Now, then what's left inside the parentheses should just be the height of each rectangle, which is just the function value at each of the different left endpoints in this case. Oh, no, sorry, this is midpoints. I said left endpoints, but this is midpoints. So what is that midpoint of each subinterval? So my first subinterval goes from x equals 4 to x equals, well, we just said the delta x, the width, is 1/2, so it goes to 4.5. So if I'm using a midpoint, then what I would plug in is obviously 4.25, 4.25. So that's the first x value that I would plug in to my function to get the actual height. And here's my function. So I need to plug in the midpoint of 4.25 from that first subinterval to get the height of that first rectangle. And I can see in these first two options, 4.25, 4.25, hey, that's what I plugged in to the function to get the height. Now my next midpoint, if I kind of go through the same logic again, between 4.5 and 5 would be my next subinterval, and halfway between 4.5 and 5 is going to be 4.75. And then keep doing that, and we're going to see these are the x values that we would plug in to actually get the height of those rectangles. So that would be A is in fact my correct answer here. As you look at the next, sorry, I said A was correct, but A is not correct. Ridiculous. B is correct because it has the correct delta x on the outside. A does not have the correct delta x. The heights of all the rectangles are good inside the parentheses, but the delta x that we factored out, the width of all the rectangles, is incorrect. So correct width, correct delta x, as well as the correct heights of each of the rectangles. C and D, this is a trapezoid method where you've got base 1 plus base 2 over 2. So this is, as soon as I see that over 2, I'm thinking trapezoid. And so I think what College Board was trying to get us to confuse here is to confuse the midpoint method with the trapezoid method. So both C and D are trapezoid methods. A and B are correct midpoint, but only one of them has the correct delta x. All right, number 2. So in number 2, it refers to the table above. That table is available on your copy of this, but it's not showing up on mine right now, so that's okay. So as we read the question here, though, A is a constant, R is the right Riemann sum approximation, which of the following statements is true? So we're basically looking for the right Riemann sum here. And as you look at the table, which you can't see on my screen, but you can hopefully see on your screen, because we're using a right Riemann sum, the very first value in the table is not going to be a part of my my picture here. I'm just going to go ahead and draw a little bit. I think that will help. So we're given the first y value. I don't know what the x values are. They're given to us in terms of a. But I'm given a first y value of 5. Let's make a dot and call it 5. And then 4. And then 2. And then 1. And then negative 1. Now, because we're doing a right Riemann sum, my first interval here, which is from a to a squared, the 5 is not a part of it. And then we go from a squared to a cubed. And then from a cubed to 10a. And then from 10a to 12a. So I'm just adding up the area of each of these rectangles. And so again, the first thing I notice as I think about this as a right endpoint rectangle is that the 5 is never one of my right endpoint rectangles. So as we look at the approximations, the first two use that 5. So they're out. Now we look at C and D. Well, they use as the heights 4, 4, 2, 2, 1, 1, negative 1, negative 1, which those are the values. 4, 2, 1, negative 1. Those are the right endpoint heights. And then I look at the width. Well, the width of my first rectangle is a squared minus a. Yes. The next one is a cubed minus a squared. Yes. 10a minus a cubed. Yes. 12a minus 10a. Yes. So the only question is this an underestimate or an overestimate? Once we got rid of this 5 because it wasn't part of the right endpoint, it's just a matter of knowing, is my right endpoint approximation an underestimate or an overestimate? And because the problem says that f is decreasing for all x, I know that my right endpoints are going to be the low end of my actual curve. Now, I don't know exactly what my actual curve looks like, but I know that it's decreasing here. There's no availability of increase. So we're going to have this missing area here with our right endpoints. And I think one of the important takeaways of this particular problem is when you look at a table like that, and obviously, again, you don't see it on my screen, but on yours, so often people are just scared of the way that that's presented with the A's. And we're like, oh my gosh, this problem is going to be so hard. Well, actually, there's only two simple little things you have to consider. Is the 5 a part of your approximation, or is the negative 1? Depending on if I would use the 5 and not the negative 1 if it was a left endpoint approximation. But since it's a right endpoint, we don't use the 5 and we do use the negative 1. And then, is it an underestimate or an overestimate based on whether the function is decreasing? So sometimes we're scared of a problem. It just looks very complicated. But as we dive into it, if we can get past the ugliness, there's often a fairly simple, straightforward way to actually do the problem. All right. In this next one, there's actually, again, a piece that's missing from mine here. I pulled this over to my iPad before I proofread, but it's fixed on the one that's posted on Schoology for you. So in this particular problem, what's missing is, from mine here, is that the x's are supposed to go from x equals 1 to x equals 7. And that's already on yours. So we're using a left Riemann sum approximating the area under this function using n intervals. And so just like in number one, I'm going to start with that length of the subinterval. The overall interval, my interval length, is 7 minus 1, which is 6. And then my subinterval length, my delta x, is that value 6 over n. And usually they tell us, we're going to do 4 subintervals or 3 subintervals, but in this case they just say n. So that's all I can do, is just leave that as 6 over n. So that's sort of what gets factored out of my Riemann sum, because it's the width of every rectangle. I'm not adding it up every time. I factor it out of my addition. And so I can see that 3 of the 4 have that delta x that I want. So I can get rid of a right away. I don't like him because of this. And now it's just a matter of looking at the function. Okay, so the function is 4 ln x plus 2. So what changes for each of my rectangles is the height, and that's based on what value for x I plug in. So all this is in here is just a way to give me the correct x to plug in. Now if we're doing a left endpoint rectangle, the very first, and so I'm going to draw a little x-axis here. Actually, go ahead and just roughly sketch the graph. The graph is going to look something like this. Okay. And we've got 1, and we've got 7. Because it's a left endpoint rectangle, the first value that I will plug in for my x is 1. Oops, that didn't look quite right. The first value is 1. I take the x of 1 and I go up and I find the height of my rectangle. So when I plug 1 over here, to get my first value in my summation into k, the output has to be 1. In this one, it would be 1. It would be 1 minus 1 is 0 over n is 0 plus 1. Okay, so that works. However, we already eliminated this choice because it doesn't have the right delta x. But this one, if you plug in 1 for k, you're going to get 6 over n. That's not 1. I need my first x value to be 1. Let's try this one. 1 minus 1 is 0 times 6 is 0 divided by n is 0 plus 1. Okay, this one works. Should have gotten rid of b there a second ago, sorry. Doesn't work because of that. D also does not work because if I plug in 1, I'm going to get 6 divided by n plus 1. Well, that's not quite right. 6 divided by n plus 1 is not the same as 1. So the answer is C. Now, I want to talk a little bit more about D because it's going to help me kind of, I think, understand a little bit better what's going on and also prepare for one where the question is a little bit different. So let's talk about what would my next subinterval be here. Well, if they told me that I was going to cut this into 3 chunks, then I know I would go over 2, 3, and then 5, and then 7, and those are my 3 chunks. 1 subinterval, 2 subinterval, 3 subinterval. But they didn't tell me that. They said we're going to cut it into n chunks, and so each one is 6 over n units long. So this next endpoint is not 3 necessarily. It's 1 plus whatever 6 over n is. And then this next one, I'm going to run out of room, so I'm going to go way down here. It's that endpoint, 1 plus 6 over n, my previous endpoint, plus another 6 over n. It's just like if my subinterval was 2, I would just keep adding 2, 1, 3, 5, 7. If my subinterval length is 6 over n, I just keep adding 6 over n. So this has to be set up here so that this inside piece has to be set up so that when I plug in 1 and then 2 and then 3 and then 4 and then 5 all the way to n, this is going to give me the sequence 1 for the first one, then 1 plus 6 over n, then 1 plus 6 over n plus another 6 over n, then 1 plus another 6 over n. And so if I just simplify this a little bit, I think we can see how this will happen. This is really going to simplify down to be 1 plus 2 times 6 over n. And then the next one would be 1 plus 3 times 6 over n. And you can see in my parentheses here, this is just going to keep going up by 1. At first it's 0, giving me just 1. Then 2 minus 1 is going to be 1, so it's going to give me 1 plus 6 over n. Then 3 minus 1 is 2, so there's going to be 2 times 6 over n, and so on. So I'm just thinking about how am I going to step out this interval here and find the length of each subinterval. How am I going to set this up so that I have the correct x values for my left endpoints, and in this case it is C. It's a tricky one, it's an ugly one, but there it is. All right, the next two problems here are fortunately no typos on my screen, so that's a good thing. Get rid of this guy here. Rewind if you need to go back and copy that down. So we can just focus on what. Let's undo that. All right. Okay, so let's just focus on this word problem here. So water flowing into the tank. They give us values of R of t, gallons per minute. Use a trapezoidal sum with 3 subintervals indicated by the table. What is the approximation? Okay, like we did in class, I'm going to draw a quick picture here. Nine, and then over to 4, 6, and then over to 7, 4, and then over to 9, 3. So my trapezoidal sum, just connect these. Use both the left endpoint and the right endpoint. And then the area for each trapezoid is 1/2 base 1 plus base 2 times the height. So for my first trapezoid, that's going to be 1/2 9 plus 6 times the height this time, which is 4, plus next trapezoid 1/2 6 plus 4 base 1 base 2 times the height, which this time is 3, plus 1/2 base 1 base 2 times the height, which this time is 2, from 7 to 9. Add all that up, get your answer, and we get 52. And so we think, okay, yay, I got 52. That's answer A. How nice. But the 52 does not represent how much water is currently in the tank. That represents how much water entered the tank. Because we're saying, okay, this is how much is going in from time t equals 0 to time t equals 9. But we also started with 15 gallons of water. So we have to then add 15 and get 67. Got to read the problem carefully. Like I said, in class, you want to read the problem carefully, figure it out, but then be able to say, okay, let me ignore the situation for a second, find my approximation, and then go back, read the problem again, double check, did I actually answer? Okay. Next one. So again, we have a table here. In this case, they ask us to do something a little different, kind of a little throwback review for us here, using a tangent line approximation. So I write my tangent line. Y minus y1 is equal to m times x minus x1. Now they're asking us for this at x equals 4. So that's my x1. In the problem, they say at, or sorry, not x, but t, at t equals 4, the length is 5. So that's y minus 5. And then also then at t equals 4, the slope, the derivative, is 0.8. So I plug that all in, that's my tangent line, and I'm using that to approximate the length at 4.3. Or at time t equals 4.3. So that's going to be y minus, I'm just going to say y equals 0.8 times 4.3 minus 4 plus 5. And I think we're going to get 5.24. You might have to double check my math there. Then it also asks, is this an overestimate or an underestimate? Well, with a tangent line, it's all about concave up or concave down, and they say that this function is concave down. If I have a concave down function, and I draw the tangent line, it's going to be above the curve, okay, despite my squiggles. So that means it is an overestimate because L is concave up. Now, part B, use a left Riemann sum with the 4 subintervals indicated by the data to approximate the area underneath L prime. So we just set up our Riemann sum here. Not too bad, hopefully. Okay, I'm going to get rid of my work for part A, so pause, write it down, rewind if you need to. There we go. Nope. Not what I wanted. Just that. There we go. All right, part B, left Riemann sum. So it's going to be 1 times 2 plus 0.8 times 3, because that's going from 4 to 5, plus 0.7 times another 3 from, wait a second, I did that backwards, sorry. This one should be from 4 to 5 is a 1. Then 0.7 from 5 to 8 is times 3, plus 0.4 times 2, going from 8 to 10. Add all those up, get your Riemann sum. My units here would be feet. Like we said in class, if you put those units on your arithmetic, each time you multiply a y value in feet per week times a t value in weeks, you're going to be left with just feet, and then you add feet plus feet plus feet plus feet to get feet. Is our answer this time an underestimate or an overestimate? Well, we used a left endpoint approximation, and we know that that being an underestimate or overestimate depends on whether the function is increasing or decreasing. And we know, because the derivative is positive, the function would be increasing. So my left endpoint would be an underestimate. Underestimate, because L is increasing. And we used left endpoints. All right, so there's tonight's homework.